Hello teachers, we're going to talk about chapter 3, this time section 3-2, addition of whole numbers. And in this video, we want to talk about number relationships, including comparing and ordering, the meaning of addition by studying various models, properties of addition and how to use those properties, several addition algorithms, including the standard algorithm and how to use them to solve problems, addition with number bases other than base 10, mental addition, computational skills, and estimation. So when you want to talk about a set model is one way to represent addition of whole numbers. Suppose Jane has 4 blocks in one pile and 3 in another. If she combines the two groups together, how many objects are there in the combined group? So this gives you a wonderful visual image of exactly what's going on with addition. Note the sets must be disjoint, which means they have no elements in common, or an incorrect conclusion can be drawn. So notice our diagrams here are separated. There are no elements in both. If there were elements in both, you couldn't just add the cardinal number of set A plus the cardinal number of set B, because they would have some in common that you would be adding twice. But as long as the sets are disjoint, it's just the number in A plus the number in B. In this case, the number in A is 4, and the number of B, or the cardinality of B, is 3, and 4 plus 3 is equal to 7, which is the number in A union B. And that really brings us to the definition of addition of whole numbers. It's just the number in A plus the number in B, and that's equal to the number in A union B. But very important, the sets must be disjoint sets to be able to use that idea. All right, what if the sets are not disjoint? How do you handle that? So remember, in set theory, if sets A and B have values in common, the number in A plus the number in B, you have to subtract out what they have in common, because that you've already added it in twice. You subtract out the intersection of A and B, and then that's going to give you the number in A union B. And I've got an example for you which might help you with a homework problem. So it says if the number of B is 2 and the number in A union B is 6, what could be the cardinality of A? All right, so let's just use our formula. So we know that the number in A, or the cardinality of A, plus the number in B, or the cardinality of B, minus the number in the intersection is equal to the number in the union. Okay, we don't know if these sets are disjoint or not, so if we don't know, we're going to have to subtract out the intersection. Now we know, again, let's fill in what we know. The number in A plus the number in B, remember they told us is 2, and then we have minus, we don't know the intersection, or even if there is an intersection, and that's equal to the number of A union B is 6. Now what we need to imagine is what could be the cardinality of A to make this true. Now if we knew that the intersection was equal to 0, we would know that the number in A would have to be 4, right? 4 plus 2 is equal to 6. But that's if the number in the intersection is equal to 0, which means they're disjoint. So, 4 is a possible answer. On the other hand, what is the largest the intersection could be? What's the absolute biggest the intersection could be? Well, it can't be any bigger than 2, right? Because the number in set B is 2. And if all the elements of B are also in A, that means the number in A intersection B could possibly, at most, be 2. So I'm going to write that underneath there, all right? So it would be the number of A plus 2 minus 2 equals 6. So those 2's would cancel out, which means the number in A could also be 6. Now that's the most it could possibly be. Also, it could be between there. So it turns out that the number in A could be 4 or 5 or 6 for this to be true. Again, if the intersection is disjoint, the intersection B is 0, so 4 plus 2 is 6. On the other hand, the intersection could be possibly as big as B, no bigger, right? Because you can't intersect and have things in common any bigger than it's in the set itself. And so we considered that extreme. Those would cancel out, and you could have 6 is a possibility for A. That's going to help you with a homework question. That's why I did that problem. Now let's talk about the number line model. Let's just say that Kenzo has 4 feet of red ribbon and 3 feet of white ribbon. How many feet of ribbon does he have altogether? So if you come down on your number line and you have 4 feet of red ribbon plus 3 feet of white ribbon, you see if you stack those up, addition on the number line, and on the number line addition means move to the right, then you're going to have 7 feet. And you see that right there on the number line. 4 plus 3 is equal to 7. Or you could have an example. One day Laura drank 4 ounces of orange juice in the morning and then 3 ounces at lunchtime. If she drank no other orange juice that day, how many ounces of orange juice did she drink for the entire day? And we could again add 4 plus 3, and that would give you 7, depicted on the number line. Considering the number line model, students need to understand that the sum represented by any 2 directed arrows can be found by placing the endpoint of the first directed arrow at 0, and then joining to it the directed arrow for the second number with no gaps or overlaps. The sum of the numbers can be read. So again, if we go look at the picture, that's exactly what happened. We connected the first arrow starting at 0 and then to 4. And then if I change colors on you, the second arrow starting at 4, 3 units long, and that gave us our result of 7, just like it said. Let's talk about the definition of less than. So for any whole numbers, A and B, A is less than B, written as, and you read that the same way, A is less than B. Again, you think about this like an alligator. The mouth is open towards the larger number. So A, you read it left to right, is less than B. If and only if there exists a natural number K such that A plus K equals B. Right? If you look at that on a number line, A is some number smaller than B, and there's going to be, as long as A is smaller than B, there's some number K, would be the distance between A and B. A is less than or equal B means A is less than B or equal to B. A is greater than B is the same as B is less than A. So you can switch them around. Again, mouth is always open to the larger number. The strategy of counting on is an addition strategy where addition is performed by counting on from one of the numbers. For example, 5 plus 3 can be computed by starting at 5. You'll see a lot of kids do this on their hands. Starting at 5 and then counting 3 more. So 6, 7, 8, 3 more times. The addition of 7 plus 4 can be performed by starting at 7. And then again, you count on 4 times. 8, 9, 10, and then the result is 11. Doubles is another strategy students use for remembering addition facts. Use of doubles, such as 3 plus 3, receives special attention. After students master doubles, doubles plus 1 and doubles plus 2 can be learned easily. For example, if a student knows 6 plus 6 is equal to 12, then using the associative property, which we're going to talk about shortly, 6 plus 7 is equal to 6 plus 6 plus 1. So you've got your doubles right here. Notice you associate those two together. You've got your double plus 1, which gives you 13. That is a great strategy to get students to quickly learn addition facts. Making 10, another strategy is that of making 10 and then adding any remaining. One way to use 10 frames to make a 10. To use 10 frames to make a 10. I didn't read that properly. One way I like to think about that is if you have, for instance, 7 plus 5, we know that 7 plus 3 is equal to 10, right? And 5 is 3 plus 2. So we have 10 plus 2 more gives you 12. That's actually the way I do a lot of my calculations and don't even really realize that I'm doing that. And you might do the very same thing. So closure property of addition of whole numbers. If A and B are whole numbers, then A plus B is a unique whole number. A and B are called the add-ins. The closure property implies that the sum of two whole numbers exists and that the sum is a unique whole number. So addition is closed within the whole number system. As long as you add two whole numbers, your answer is always a whole number. But is every operation closed in the whole number system? That's something that you need to think about. You know, what about subtraction? What about multiplication? What about division? We'll handle all those questions separately, but be thinking about these things. When you get a property, does it apply to other operations? But we know if you add two numbers in the whole number system, you get a brand new whole number. So we want to talk about whole number properties. What are things that we can do with whole numbers? Can we change the order when we're adding? And the answer to that is yes, and that's called the commutative property of addition of whole numbers. We know that when you add 2 plus 3, that is equal to 5, and so is 3 plus 2. The order that you actually add whole numbers in doesn't matter, which means there is a commutative property. We talk about the word commute means to move around, and so we are allowed to move around our addition. Again, does this property apply to other operations, subtraction, multiplication, division? Be thinking about these things as we go through the properties, and we will address those questions individually. But notice, if we look at it on a number line, we could see that clearly you get the same result. If you take 3, remember you start at 0, and then right there at the end of the arrow, you start with your next add-in, 5. 3 plus 5 ends up at 8. And can you switch it around? Could you start with 5 at 0, put 3 directly at the end, and add 3, and that also ends at 8. Or you could work with blocks. Notice over here, 3 plus a 5 length block added to a 5, is the same as a 5 plus a 3 length block. And that is the commutative property of addition. Commute, again, you think about what commute means. Your travel back and forth, say to work. It means to move around, and you can move your numbers around. What about an associative property? Does addition have an associative property? And what does associative property mean? Well, you're associating different numbers together. So if we're adding A plus B plus C, is that the same thing as adding A plus B plus C? And notice, look, that it is, right? A plus B plus C, you can regroup and add A plus B plus C. We can make up an example and say, for instance, 2 plus 3 plus 7. Is that equal to 2 plus 3 plus 7? Well, 2 plus 3 is 5, plus 7 is 12 on this side. Is that equal to 2 plus 10? 12 on that side? Sure it is. That is the associative property of addition. Then we have the identity property of addition of whole numbers. What does that mean? Well, an identity or an additive identity is a number that we could add to a whole number just to equal itself. But you have to be able to commute these. So notice you have to read this in both directions. A plus 0 does equal to A, but you have to be able to reverse it. 0 plus A always equals to A also. And 0 is what we call the additive identity. So we need to be able to identify the properties as we're doing problems. Notice here 6 plus 8 equals to 8 plus 6. We know that's true, they're both 14, but what property have we used here? Notice we have moved the 6 and the 8. The 6 was first, and then the 8 was first next. That's the commutative property of addition. What about 1001 plus 834 is a unique whole number? What property is that? That is the closure property, right? If you add two whole numbers, you always get a whole number as a result. 3 plus 6 plus 9 is equal to 6 plus 3 plus 9. Now, notice what's happening. The 3 and the 6 are grouped together here. The 6 and the 3, the same numbers are grouped together. What actually happened is we arranged the order differently. So once again, that is the commutative property of addition. Next example, 8 plus 5 plus 2, 2 plus 8 plus 5. Okay, now look what's grouped together. 8 plus 5 is grouped together here. 8 and 5 are grouped together here. So we didn't change the order there, we didn't change the grouping. What we did change is this order. 8 plus 5 was first here, 8 plus 5 is second there. That's once again the commutative property. And they say that's the associative property of addition as well. Why would you say that's the associative property? Well, what we didn't do is look down here at the end. We associated the 8 and 5 here, but in the second part, we associated the 2 and the 8. So we use the commutative property first, and then we use the associative property next. Then we want to spend some time talking about our addition algorithms. Notice we have what's called a concrete model. This is when we're using our base 10 blocks. And you'll recall with base 10 blocks, you have a block, which is 1,000. Then you have a flat, okay, which is really, we should start small, shouldn't we? So 1 unit is just a single block like this guy right here. And then 1 long is 10 units. And then a flat is 10 longs. And then a block is 10 flats. And so we could talk about various sizes here and add, subtract, multiply, divide. We'll be able to do all that with our base 10 blocks. But 14 would be a long, which represents 10, and then 4 units. And we add that to 23, which gives us 2 longs to represent the 20 and 3 units. Now you can visually see that we have 3 longs, and then we count our units. There's 7 of those, so the answer must be 37. Next we have something called the expanded algorithm. Okay, so notice what's happening here. We're going to add our 1s together, and we get 7. So we've got 4 plus 3 is 7. And then we're going to add our 10s together. So we've got 10 plus 20, and that's equal to 30. And then finally we can add our 1s and our 10s together. That's the expanded algorithm. Whereas the standard algorithm, you add the units place. 4 plus 3 is 7. Then you add the 10s place. 1 plus 2 is 3. But now sometimes with the expanded algorithm, or even the standard algorithm, you have to regroup. Now the term regrouping really is what in the past you've probably called carrying. It's the same idea as carrying, you're just regrouping. So here's what we're saying. 7 plus 8 in the expanded algorithm is 15. You could just write down 15. Then you add your 30 plus your 20 is 50. And then you're allowed to add your 15 and your 50. And notice how your place values line up. And that gives you 65. That's the expanded algorithm. Makes it very clear what's happening when you add. Whereas the standard algorithm with regrouping, notice we're going to add the 1s place first. We know 7 plus 8 is 15. So we put the 5 in the 1s place, and then we regroup the 10s. And it goes, of course, in the 10s position. And then we add 1 plus 3 is 4 plus 2 is 6. And so in the past we've called that carrying, but really it's the idea of regrouping. You have more than 9 units. So instead of putting them all in the ones place, then you turn your 15 units into 1 long and 5 units, and you carry that long up the top, and 1 plus 3 is 4 plus 2 is 6. Now what if we need to add 2 3-digit numbers? So we're going to take 186 and we're going to add that to 127. Let's look at our base 10 blocks. So 186 we're going to write as 1 flat, and then we have 8 longs to represent 80, and then you'll see over here your 6 units. And then for 127, once again 1 flat, 2 longs to represent the 20, and then 7 units. Now when we add our units, we've got 6 plus 7, and that gives us 13, right? Well, we're going to trade in. In other words, we're going to regroup. We're going to trade in these red squared off 10 units and turn that into a long. And then we're going to combine our longs together. And you see that we have more than 9 longs as well. So if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that'll turn into a flat. So we're going to trade in our 10 longs for another flat here. And our final answer is, notice we have 3 flats, so that's 300. We have 1 long, so that's a 10, and then 3 units, which makes that 10 a 13. So our final answer, 313. I think you could see that clearly with the base 10 blocks, right? Now here's an entirely different algorithm. We call it partial sums. It could also be called the left to right algorithm. Notice what we did first here. We added the first digits, the hundreds digits. So we're looking at 500 plus 700. That gave us 1200. Then we're looking at the tens. You have 60 plus 50, which is 110. Then you look at the ones. 8 plus 7 gives us 15. And then we just add down, so that's 1,325. So the traditional way that you've been used to adding, your whole life, that's just one method, probably the most efficient without a doubt. But there are other ways to think about adding numbers together. I even have another one for you. This is very interesting, called the lattice algorithm. Okay, so notice what we're doing here is we're adding 3,567 plus 5,678. And notice what's terribly important here is no matter what is to line up your place value. Every method we've used that really comes into play, unless you're working with the base 10 blocks and then you're just looking at the blocks. So with this lattice algorithm, we're going to add 7 and 8, and that gives us 15. Now how are you going to write that? Okay. So you're going to have a big rectangle down here at the bottom, and you could even fill the whole thing in. Let me show you. This shows up one piece at a time, but let me show you what you could write immediately. You can draw a big rectangle like this. Okay, and then when you add 7 plus 8 is 15, you put, of course, 15 where the tens place is higher here. Now, watch this again. I'm going to add 6 and 7. That's 13. So I'm going to have a block, 13. Okay, and I'm going to do it again. 5 plus 6 is 11. And then 3 plus 5 is 8. And we don't have anything to go there. We could put a 0 there, or 0, 8. Now, how does this work? Well, look. Here, the 1 plus 3, that's 4. 1 plus 1, 2, 8 plus 1, 9. So my answer is 9,245, but I have this done step by step. So again, we added 7 plus 8 is 15, so tens, ones, and then 6 plus 7 is 13, again hundreds, tens, and you add the tens here, 4, 5 plus 6 is 11, again, that's thousands and hundreds. You add the hundreds to get 2. And then finally, 3 plus 5 is 8. And so you add the thousands together, and then you don't have any 10,000s to carry over here. So it's another interesting way of adding numbers together. How about column addition? In the column addition algorithm, we add the numbers in each column, writing each sum directly beneath the column. Then we regroup each place one column at a time. Base 10 blocks are often used in the column addition algorithm. So here we have an example. Okay, so we're adding 568. So notice here, 568 plus 357. And we have columns specified for hundreds, tens, and ones, and 568, 357. You add the ones, you get 15. Okay, you add the tens, and you get 11. And you add the hundreds, and you get 8. But then we need to regroup. So the 15, right, is 5 ones. And we're pulling out the 5 ones comes down here, and then the 1 comes over here to add to the 11 to make that 12. And then here, right, we keep the 2, and one of those comes over here to make that a 9. And that gives us 925. And again, it's very similar to this idea of carrying that we've done in the past, and we're calling that regrouping. Now let's check out the opposite change algorithm. It's interesting. So the opposite change algorithm for addition, we decide which add-in is closer to a nice number. It's either typically 10 or a multiple of 10. In other words, you're trying to get to 10 or 100 or possibly even 1,000. Then decide how to adjust that add-in so that it ends in 1 or more zeros, and adjust the other add-in the opposite direction. The goal is to make the addition problem a problem without the need to regroup. And I bet this is something that you have done when you do mental calculation before. So watch this, okay? So we're going to add 189 to 278 right here, okay? Now 189, you notice, is close to 190. So I'm going to take 189, I'm going to add 1 to it, and that's going to make it a 190. Now, I have to fix that. I can't just add 1 to it. So to make that adjustment, I'm going to subtract 1. And so 278, when I subtract 1, that's going to give me 277. That's where we are now. So add 1, subtract 1 to keep it balanced. Now, the next trick, I'm at 190. Hey, I could even go up to 200. So I'm going to add 10, but then I've got to subtract 10 from the 277. So now I'm at 200, and then 277 minus 10 is 267. But mentally, that's easy to do. 200 plus 267 is 467. You can also write it down like we did here. So this opposite change algorithm means you add to one and you subtract from the other, and that still gives you the same result as just adding the two numbers together. So it's an interesting way to go, and sometimes quite valuable, especially if you're doing some mental math. Now this one, never seen this before, but it's an interesting algorithm. So you add the numbers in the units place starting at the top, like tradition, right? But we do 7 plus 5, that's 12. So watch what happens, okay? When you get to a number over 9, then you scratch out. So we're scratching out the 5 and replacing it with 2. And then I add 2 plus 9, and I'm going to scratch again because 2 plus 9 is 11. So I'm going to scratch through and say that's a 1. Now, you might be wondering about the carry and stuff, okay? Well, notice I have 2 scratches now. You count your scratches, and that's what carries to the other side. So I've got 2 scratches, which means that's where this 2 at the top comes from. And now I do it again. I add 2 plus 8, that's 10. So I scratch out the 8, replace it with a 0. 0 plus 6 is 6. 6 plus 4 is 10. I scratch out the 4 and make that a 0. Notice I've got 2 scratches. Okay. Then that's going to be a 2 that we carry over here. And then remember we ended with a 0 down here. Okay. So again, when the first column of addition is completed, write the number of units, 1 below the addition line in the proper place value position. Count the number of scratches, 2, and add this number to the second column. Then we do it again with the first column. Repeat the procedure for each successive column until the last column with non-zero values. Okay, so we ended with a 0 right here. At this stage, sum the scratches and place the number to the left of the current value. So the scratch method is a very interesting way of adding. Now I've reached my limit for this video, so I want to come back. I don't have a huge part 2 video to do, but we do want to talk about adding numbers that are not base 10. So that's worth coming back for part 2 of the video. I hope you have a great day. If you have any questions about these algorithms or any addition properties, please let me know and I'll try to make anything I can clear. Have a great day.